Now we'll look at two examples to show how factoring can be helpful when determining limits. Notice in both cases, we have the limits of rational functions. First, we have the limit as x approaches 2 of the quantity x squared minus x minus 2 divided by the quantity x squared plus x minus 6. Before we factor this, though, let's look at the graph of this function. Notice how the rational function has a hole at x equals 2, or it has point discontinuity, and it has infinite discontinuity, or a vertical asymptote at x equals negative 3. So because this function is undefined at x equals 2, we could not perform direct substitution to determine this limit. We'd have a 0 in the denominator. So let's go ahead and factor the numerator and denominator to better understand the graph of this function. We'd have the limit as x approaches 2, and then the numerator is going to factor into two binomial factors, and so will the denominator. So to factor x squared minus x minus 2, we'll have x and x. The factors of negative 2 that add to negative 1 would be negative 2 and positive 1. And then for our denominator, we'd have x and x. And the factors of negative 6 that add to positive 1 would be negative 2 and positive 3. So notice how we have this common factor of x minus 2, and the zeros of the common factors produce holes in the graph as we see here. But remember, having a hole here at x equals 2 does not mean the limit does not exist. In fact, graphically we can see as we approach positive 2 from the right side or positive side, and as we approach positive 2 from the left side or negative side, we are approaching the same function value, and therefore this limit does exist. But because we have the function in factored form now, we can actually simplify out the common factor here, which would give us the same graph without the hole, and therefore in the simplified form, we can perform direct substitution to determine this limit. This limit would be equal to the limit as x approaches 2 of the simplified function of the quantity x plus 1 divided by the quantity x plus 3. So if we perform direct substitution now, we would have just 2 plus 1 divided by 2 plus 3, or 3/5. Our limit is equal to 3/5, meaning as we approach x equals 2 from the left and the right, we are approaching the function value of 3/5. Remember, the function values are the y values. Now looking at our second example, let's go and jump to the graph. Notice how the function is undefined at x equals negative 2. Once again, we'd have division by 0. But looking at the graph, notice here where x equals negative 2, we can graphically see the limit does exist. As we approach negative 2 from the positive side or right side, and as we approach negative 2 from the negative side or left side, we can see from the graph we are approaching the function value of 12. To find this limit algebraically, once again we'll factor the numerator and denominator. So we have the limit as x approaches negative 2. Now the denominator does not factor, we have x plus 2. But the numerator is a sum of cubes, which we can factor using this formula here. Or in our case, a would be x, and b would be 2, since 2 cubed is 8. So we would have the quantity x plus 2. Again, for our purposes, a equals x, and b equals 2. So for a squared, we'd have x squared. And then minus a times b, that'd be minus 2 times x, or minus 2x. And then plus b squared, that'd be plus 2 squared, or plus 4. Notice in factored form, we do have a common factor of x plus 2. Notice the 0 of these two factors is x equals negative 2, which is where the hole occurs. So now we can simplify out this common factor and use the simplified function to determine this limit algebraically. This limit is equal to the limit as x approaches negative 2 of x squared minus 2x plus 4. Performing direct substitution, we would have negative 2 squared minus 2 times negative 2 plus 4, which would just be 4 plus 4 plus 4, which is equal to 12. So when determining limits of rational functions, it's often helpful to factor and simplify, which then often allows direct substitution to determine the limit. I hope you found this helpful.